So if we look back the recent mutation-based fudging techniques, we can view that each technique serves the problem of optimizing an important strategy in mutation-based fudging based on the learning. For example, to find an optimal seed mutation strategy, MOPT and CMFudge presented a customized particle swarm optimization algorithm and a multiple armed bandit problem, respectively. Likewise, for finding an optimal seed scheduling strategy, EcoFudge presented a variant of adversarial multi-armed bandit algorithms. So I think you can also come up with a very trending solution by converting or reducing your domain-specific problems to these suitable learning algorithms. Okay, now let's move on to another gray box testing techniques, generation-based fudgings. Compared to the mutation-based fudgings, I will show you the difference of the generation-based fudging at a high level first. First, this generation-based fudger takes a specification as an input, while mutation-based fudging takes a settable, well-structured seed inputs as well. That is, a generation-based fudger does not require a seed pool like mutation-based fudgers. Also, since this generation-based fudger is to generate test case from a given specifications, each test case generator will also be different from the generator of the mutation-based fudgers that slightly change the selected seed. After generating the test case based on its own generators, the rest of the process is pretty much the same for the two different fudging techniques. This fudger will execute the binary of the target program with this generated test case and measure the code coverage or check the bug finding and go back to the generators and repeat the process of generating test cases based on their criteria and executing the binary with these generated test cases until the testing budget expires. That is, the key difference lies in the specification as the input and the test case generation method from the given specifications. More specifically, this specification usually refers to the grammars that express the valid inputs for the target programs. In other words, grammars express the syntactical structures of the inputs like JavaScript or MP3 files. And these grammars are usually consist of a start symbol and a set of expansion rules. More specifically, an expansion rule denotes that the symbol A on the left side can be replaced by the string B on the right side. For example, let's consider these simple grammars. In these grammars, the start would be replaced by digit based on the first expansion rules. Again, digit can be replaced by the number string from 0 to 9 based on the second expansion rules. And as you might already know, this operator highlighted in the green denotes the alternatives, meaning that any of the digits can be selected for an expansion. So each digit would be expanded into one of the given digits from 0 to 9. So that is using these example grammars, the test case generator is able to generate a string between 00 and the 9, from the 00 to the 99. And this previous grammar only expands to a finite about 100 test cases. But a more realistic grammars can be recursive. That is, expansion can reuse of the symbols expanded earlier. For example, let's consider the second expansion rule about integers. And as you can see, our integer can be either replaced by a single digit or a digit followed by another integers. For example, the number 0122, which is my birthday, would be represented as a single digit and followed by integer 122. And this integer 122 is digit 1 and followed by integer 22. And this integer 22 consists of a digit and another digit 2. In other words, based on this recursions, this grammar has an infinite space of the test case to generate it. Let's look at a more complex grammar which can cover full arithmetic expressions. Let's consider a test case depict 1 plus 2 multiplied by 3.4 divided by 5.6. To generate this test case, starting from a start symbol, it expands to an expression on the right based on the first rule. And then this expression can be one of the three alternatives, a term plus expression and term minus expression, or just term. And let's expand just term. And then this term has also three alternatives. And let's select the first one terms time, which is the term time multiplies factors. And again, let's replace the left terms into the factors. And in this way, if we continue to apply the extension rule that replace the symbol on the left with the symbol on the right, it will be possible to extend depicting 1 plus 2 multiplied by 3.4 divided by 5.6. And what should pick up on this slide is that generating test case from this grammar for arithmetic expression that is much simpler than describing actual program syntax, but it seems very complicated. That is, research topics in the generation-based fudgings can be divided into two main questions. The first topic is about how to build a good grammars for effectively explaining the syntactical structure of the inputs. And the second one is about how to expand from a given grammar due to the huge search space of the expansion rules. And the diverse techniques for the generation-based fudging tries to solve each research topic independently or both topics simultaneously. Okay, let's take a closer look at each research topics. The first topic is related to the test case generator, where its job is to determine how to expand the rules in a given grammars. And as you can see from this complex derivation tree, this infinite search space is the challenge of the first research topics. And like the search heuristic of the symbolic execution to mitigate the policy explosion problems, a smart generation from the given grammars in generation-based fudging is essential for maximize code coverage or finding complex bugs within a finite or reasonable time budgets. And let me show you a concrete one evidence for the need of smart generations. Using a grammar-based open source fudger named grammarinators that randomly expands the expansion rules, I tried to generate the JavaScript files based on the left grammars. And for considering the full grammars, this grammar is quite complex and consists of hundreds of lines for describing these grammars. And my question is, how many useful JavaScript files this grammar-related fudger can successfully generate from this grammar through the random derivations? Can you guess the percentage of the useful JavaScript files? As you can see on the left pie chart, the random generation method from that grammars succeeded in generating only 1% of the valid JavaScript files. And as you can see on the right, even these 1% valid inputs are also mainly made of very simple JavaScript files that are syntactically valid but not helpful for discovering the hidden bugs. In other words, smart generation from a given grammar is essential process. And second, I also brought an example of the invalid input. This test case depicting return bar 1 equals to the 4 plus 3 is invalid because the return statements are only valid inside the functions. That is, a return statement that is not in the function is unnecessary input. So, but the grammar does not describe the function statement expand first and then the return statement expand within this function statement. As a result, due to this insufficient grammars knowledges, a lot of redundant JavaScript file will be generated during fudging. So building a good grammar is also essential process for enhancing the overall performance of generation-based fudgers. Okay, let's summarize these lectures now. We first explore the seed scheduling algorithms, which is one of the key components of the mutation-based fudgers. And this seed scheduling algorithm aims to smartly select a promising seed first from the seed pool and smartly decide the number of mutants generated from the selected seed. And second, the recent works for mutation-based fudging aims to solve the problems by presenting a domain-specific learning algorithm for each fudging task, such as finding an optimal seed mutation strategy or seed selection strategy or seed allocation, energy allocation strategies. Lastly, we explored another style of gray box testing method, which is the generation-based fudging. And its key components are about how to build good grammars and how to expand from given grammars. Okay, this is the end of these lectures. Thank you for listening to these lectures. Okay, goodbye everyone.